Hello everyone, my name is Muhammad Azri bin Yahya, a representative from UiTM Shah FRGS, together with my supervisor Dr. Shuzlina and Dr. Sophie, has worked on a research with the title of Object Detection for Autonomous Vehicle with LiDAR using Deep Learning. Deep Learning in this study is YOLO V2. In this video, I would like to explain what our research are all about. Without further ado, let us get started. In this era, we know that autonomous vehicle is becoming popular among the car industry, not only in other countries but also in Malaysia. It's currently making a way to make an autonomous vehicle production. We can take a look at New Proton, where they announced a new model called X50, where it can autonomously drive with a level 2 autonomous, but not fully automatic yet. Even though this technology is promising, it is vital to focus on the safety aspects of the autonomous vehicle to avoid any accidents or collision with objects during the navigation, to protect the people inside the vehicle itself, and the people surrounding it. The effectiveness of camera sensors with visual perception is diminished in dim lighting because most vision have limited functionality at night. The performance of autonomous vehicle with camera sensors for object detection is still dependent on less efficient algorithms such as Region Convolutional Neural Network (RCNN) and Single Shot Detector (SSD). RCNN uses selective search that reduces the number of bounding boxes to the classifier up to 2000 regions, and SSD has a problem in detecting small objects. Now we go to the problem statement. The first problem is the camera is like our eyes. We cannot see in the dark, and if it's raining heavily, it is so hard to see. The camera is also when you take a photo and it's only in 2D images. This will cause a problem when it tries to detect an object, but the object is overlapping with another object. Camera sensor cannot map the environment as it has a limited view. To be able to see a 360 degrees view, it needs to have a multiple camera sensor, and it will cost more. In our literature review, we had researched several papers, and we focused on a paper with autonomous vehicle to see how the autonomous vehicle works, object detection on how do they detect the objects, object classification on how do they classify it is an object, algorithm used to see what algorithm they use for object detection, and what kind of sensor they use in detecting the objects. Now we go to the methodology. When we collect data using the LiDAR sensor, it will save as a PCAP format, and this collected data needs to undergo two conversions, and that is CSV format and the BAG format. CSV format is used for data analysis, and the BAG format is used for model development for object detection. After the conversion, the BAG format data will be pre-processed so that it can proceed to be used in the model development. There are three pre-processes need to be done, and that is noise removal, downsample, and transform. Noise removal is to remove random point cloud that exists in the data. Based on figure 1 and figure 2. Figure 1 is the original data, and you can see some of the random point cloud has been removed in the figure 2. Downsample is to reduce the point cloud from the original data. Based on the figure 1 and the figure 2, figure 1 shows the original data and figure 2 shows the downsample data. The difference between these figures, downsample data has less point cloud than the original data. And the transformation includes the rotation and shearing input point cloud. Rotation creates an affine transformation object that defines 45-degree rotation along the z-axis. And shearing creates an affine transformation object that defines shearing along the x-axis. After the data is ready to use, we go to the model development. First, we use Robot Operating System (ROS) to map the data because ROS is flexible framework. for programming a robot that contains a variety of tools, libraries, and conventions that helps to simplify the task of creating a complex and robust robot behavior across a collection of other robotic platforms. Then apply YOLO V2 algorithm to the data. YOLO V2 is a real-time object detection system that uses different approaches by applying a single neural network to an image. The network divides the image into partitions and predicts the bounding boxes and probabilities. The predicted probabilities are the weight of the bounding boxes. The model is applied to the image in multiple locations to find the highest score. The image with highest scoring regions is counted as a detection. To apply the algorithm, the x and y axis of the center coordinate and the height of the box use the equation as shown in number 1 and number 2, similar to the z-axis as shown in number 3. The x and y axes are regressed by predicting a value between 0 and 1 for each grid cell in the map model. It is located where the point lies in the cell. The value of the z-axis is only mapped to the point at a vertical grid because the z dimension is smaller than the x and y dimension. The height of the box uses the equation in number 6, similar to the width of the box shown in number 4 and the length shown in number 5. Data 1 result is a detection for single pedestrian to test whether or not the YOLO V2 algorithm can detect a simple object. As you can see, the first terminal is a coordinate for each vertex of the bounding boxes, and the second terminal is the LiDAR view, and the third terminal is the camera view. Data 2 shows a detection for multiple vehicles on a highway to test the SSD algorithm for its accuracy. For now, both YOLO V2 and SSD are 100% accurate in detecting simple objects, such as pedestrian and vehicle. To prove YOLO V2 is better than SSD, both algorithms were tested with the same setting of 7 objects in single frame. Data 3 result shows the detection of both pedestrian and vehicle for the YOLO V2 algorithm. 5 out of 7 objects were detected by the YOLO V2 algorithm, constituting 71.43% accuracy. However, the result of SSD was not as good as YOLO V2. As seen in data 4, only 4 out of 7 objects were detected by the SSD algorithm, constituting 57.14% accuracy. This result concludes that YOLO V2 performed better than SSD algorithm. The table shows the summary result of data 1 to data 4 by comparing the performance of YOLO V2 and SSD algorithms. The analysis is done based on the different number of objects the camera viewed and the number of objects detected by the algorithm. The table also shows the time in seconds taken to complete the detection of all objects in a single frame. YOLO V2 has the fastest time in object detection compared to SSD. It also shows that YOLO V2 has better accuracy than SSD. The result also shows that the more objects present in single frame, the harder it is for both algorithms to perform detection. In conclusion, this study demonstrates the development of object detection model using LiDAR point cloud data for object detection by applying algorithms such as YOLO V2 and SSD. The result shows that YOLO V2 performs better than SSD algorithm in detecting objects. It also reveals that YOLO V2 is faster in detecting objects in a single frame compared to SSD. Thus, our result concludes that YOLO V2 is better than SSD in object detection. The result of this study can act as a preliminary investigation for those who are interested in autonomous vehicle, particularly in object detection. For future work, can modify the algorithm for loop closure so that it can be applied or tested for real-time detection with a greater number of samples and experiments. Furthermore, by adding more sensors and visual aids like cameras during data collection, this can ensure the performance of the model is in excellent condition. That's all for me. Thank you.